Hey y'all, welcome everyone to week 8 of BUSS1020. So in week 8 of BUSS1020, we talk about one sample hypothesis testing. So one sample hypothesis testing is very loaded. There's a lot to talk about, a lot of formulas, a lot of concepts, a lot of foreign concepts if you have not learned statistics previously. There's a lot of foreign concepts, a lot of here and there, a lot of rules to keep track of, z-test, t-test, critical values, rejection regions, type 1, type 2 errors, a no alternative hypothesis. So a lot of concepts and a lot of new information to take in. However, this is also a very foundational and a very cornerstone week and a very cornerstone unit. Week 8, which is this video, we're talking about one sample hypothesis testing. Week 9, we're going to be talking about two sample hypothesis testing. So, and then week 10 and 11, we talk about a regression. We also have hypothesis tests within regression for the mean and a population proportion. So, yes, the content is very hard. The content is very tough, but this is very cornerstone. So sooner or later, you're gonna have to be able to learn these concepts. So, okay, enough of me rambling around. Let me turn my camera off. And then let's get into week 8's content. Let's just quickly look at the modules first, and then of course we're gonna go look at the Excel for the tutorial, as well as my notes. For this week. So first of all, hypothesis testing, one sample test. We're going to have an introduction to concepts of hypothesis testing. If you did not do statistics, if you did not have statistics in high school, in HSC, in A levels, if you did the IB, you certainly had some statistics, but hypothesis testing is really, has a lot of foreign concepts and has a lot of Greek letters that you have to be able to understand what they mean. We're going to also be talking about types of errors, for type 1, type 2 errors, alpha and beta. Test for the mean, one sample. Test for the mean, one sample. And then that's and a week 8 is test for the mean for one sample. We also want tests, hypothesis testing for the proportions, also for one sample, ethical considerations, and the workshop. In week 9, we're going to be talking about two sample tests for hypothesis testing. So it's really quite critical and very quite imperative that you understand the concepts and you pick up the concepts for hypothesis testing from week 8. So before we talk about concepts of hypothesis testing, here's something that's very interesting and a cornerstone of statistics and statistics notation. So, if you think about, no, that's not what I want. Alright, let me turn this off real fast. Alright, delete this. Okay, if we think about a few of the notations we have talked about, we talked about mu, we talked about x bar, we talked about sigma, we talked about sigma. We also talk about S. What else do we talk about? We are going to be talking about rho and then R. So in these cases, what we see is these right here. This is R. This is not P. This is rho, by the way. It's a Greek letter. So so what we see right here is these are Greek. Okay, these are Greek symbols, and then these are Latin symbols. So in order to differentiate between population and sample, one of the very intuitive, perhaps not intuitive, but one of the very interesting things that statisticians do is that Greek alphabets, mu, sigma, lowercase sigma, and rho, are used to describe characteristics of the population. Whereas, what the heck is happening? Characteristics of the population. Okay, that is not what I want. Characteristics of the population. Whereas Latin symbols, X bar, S, and R, are used to describe proportions and characteristics of the sample. So if you see M, if you see mu, you know that's Greek, then you know that refers to the population mean. If you say X bar, you know X bar is Latin instead of Greek, then we know that X bar refers to the sample mean. If you see standard deviation, we don't know if it's the standard deviation of the sample or the standard deviation of the population. However, because sigma is Greek, we know that standard deviation of the population is sigma instead of being S. So that's just something for us to keep in mind before we talk about hypothesis testing. Okay, so we talk about so let's just get right into it. So hypothesis testing really is a theory that asks and answers questions and claims or predictions that can be tested. And one of the most common ways to test these is with the empirical method, such as below. Now, when we talk about the empirical method, is not to get confused with the empirical rule. So the empirical rule is the idea of 68% within 2 standard deviations, 97 within 2, 99.7 within 3 standard deviations. No, that is the empirical rule. What we are talking about is the empirical method, which is the procedures and the processes of hypothesis testing. So, okay, so for example, if we want to, if I am let me see what products I have near me. Okay, I am a uni student, so of course I have heaps and heaps and heaps of Red Bull on me. So let me turn my camera on real fast. So I have heaps and heaps and heaps of Red Bull on me, and if I work at Red Bull and I want to say that each Red Bull can, as you can see, says it contains 250 milliliters. Now this is the claim, that it contains 250 milliliters of liquid content. You know, let me open one of these cans. I feel like drinking a Red Bull tonight. I'll get a chilled can. Okay. All right. I know this perhaps isn't the best use of review time, but I really wanted to make this review session a little fun, a little engaging, and a little not just me talking about statistics. I love the artificial taste of Red Bull. Anyways, so what it says is 250 milliliters per can of Red Bull, and what I could do is I could take dirty cans of Red Bull. I could take 100 cans of Red Bull out of the population of Red Bull cans. So that is when I take a sample out of the population. And I could test the sample, so I could open each can, I could pour each can out and see how much liquid is within each can of Red Bull. Now, some cans, it is impossible for it to be precisely 250 milliliters. Some may be 251, some may be 255. Of course, some may be below 250. So maybe 249, so maybe 244. Okay, so I could take a sample out of the population of Red Bull. I could take a sample out of the population of Red Bull, and see the X bar. So the X bar is the mean value. So let me close my camera. I think I've illustrated the point. All right. So and then we could test whether or not the sample lives up to the marketing claim, or lives up to the claim that there is 250 milliliters of Red Bull within each can of Red Bull. So this is the idea of hypothesis testing. We could have a claim. Okay, our claim is that each can of Red Bull contains 250 milliliters. Now, within by using statistical processes, we will be able to accept or reject this original claim. So this is where we come into play. So the first step is to state a known alternative hypothesis, H0 and H1. So H0, which is what we're trying to prove, okay, H0 would state that the mean or the mu, okay, so the mu of these Red Bull cans is equal to 250 milliliters. Whereas H1, the alternative hypothesis, would say no, these do not contain 250 milliliters. Now note that does not contain could be either mean it has more than 250 or less than 250. Okay. Second is choose the level of significance and sample size. So sample size is quite straightforward. You know, if we take 50 cans of Red Bull or if we take 100 cans of Red Bull. These are differences in the sample size. However, level of significance is denoted with the Greek symbol alpha. Okay, it's denoted with the Greek symbol alpha. However, level of significance refers to how close to the mean, how close to the mu do we want our observations to be. So we could have a 90% level of significance, 99% level of significance, but most of the time, the most popular level of significance is 95. So that would be a 5% level of significance. So which means there could be error rates. There could, if my mean population is 250.003, then of course we could accept the claim that the mean weight of Red Bull within each can is perhaps is perhaps 250. So there could be some leeway. There could be some additional fluctuations around the mean. However, we need to choose the level of significance. Also, we have to determine the appropriate test statistics and sampling distribution. So there is the z-test and there's the t-test. We're going to be talking about the differences between the z-test and the t-test. But at a very broad level, A z-test is used when the population standard deviation or the population variance is known. However, we use the t-test, which takes into account degrees of freedom when we do not know the population variance or the population standard deviation, which in most cases, in most real-world cases, we do not actually know. Okay. Step 4 is we determine the critical values. So the critical values is the values at which point we have to stop accepting the null hypothesis, and then identify rejections and non-rejection regions. Then we collect data, so perhaps we collect data from 50 or 100 cans of Red Bull, compute the test statistic, and see whether or not it falls within the acceptance or the rejection region. And then we make a statistical decision and state the managerial conclusions in the context of the business problem. So whether or not we accept the claim of H naught that there is 250 milliliters per can of Red Bull, or we reject the hypothesis that there is 250 milliliters of Red Bull within each can of Red Bull. That's the good stuff. All right. I'm not gonna finish the whole can of Red Bull. Don't worry. It's 9:44 p.m. On a Wednesday night. I won't be sleeping if I'm doing that. I cracked open a can just for illustration purposes, and y'all don't have to worry about my sleep schedule. Anyways, so if the test statistic falls within the rejection region, we reject the null hypothesis. If not, then we do not reject the null. So this is the idea of I don't know if you heard the phrase innocent until proven guilty. So this is the same idea. So when doing hypothesis testing, we assume that each can of Red Bull has 250 milliliters until the point where we can prove that we do not. Okay, prove I'm using the word prove very loosely because we cannot actually prove for certainty, because there is of course sampling error. Each sample, perhaps I just choose Red Bull cans that do not. I just very likely choose Red Bull cans that do not contain 250 milliliters. This is why as we increase the sample size, our x bar will approach the mu. Our x bar, our sample size will approach the mu, which is the population mean. And so these are concepts surrounding that. However, the idea that so this is the this would be perhaps a distribution of Red Bull weight. And as we can see, perhaps we'll be expecting the mean to be around 250, around right here. And as we go out to the either extremes, we do not have, we will have less and less extremes on either side. And if our x bar comes into play, or if our test statistic lies within the region of rejection on either side of the distribution, then we have reasonable proof that each can of Red Bull does not contain 250 milliliters because it either has too much or too little. Now, the determinant of where these regions of rejection lies all comes down to the critical. All comes down to the all come down to alpha. So alpha, of course, refers to the level of significance. So if we have a larger level of significance, which means a larger alpha, the regions of rejections would be further away from the mean. However, if we have a really small alpha, which means we have really close regions of rejection closer towards the mean. All right. So null hypothesis states the default or status claim or assertion about the population parameter. So thinking about the Red Bull example, what is the default and status quo claim? So default and status quo claim is that there's 250 milliliters of Red Bull per can. Okay. However, the alternative hypothesis opposes the null hypothesis. So what is the opposite of mu equals 250? Well, of course, the opposite of mu equals 250 would be mu doesn't equal 250. So that would be our no and alternative hypothesis. Okay. One of the things that you can really keep in mind is that no hypothesis must always contain equal signs. So it could be equal, it could be greater or equal, or it could be lesser or equal. However, no hypothesis must always contain an equal sign. So that's just something to keep in mind. It's just an additional rule to keep in mind. So there are so many damn rules within concepts of hypothesis testing. It's a little ridiculous. But yeah, just know that. All right, let's talk a little bit about as we talk about critical values. All right, let's talk about type 1 and type 2 error. So type 1 error occurs if you reject the null hypothesis. However, the null hypothesis is true. Now, Type 1 and type 2, these errors will occur for a variety of reasons. For example, a type 1 error could occur because your sample is not an accurate representation of your population. However, an example, okay, so type 1 error is when you reject null hypothesis when null hypothesis is actually true. Now, back to the Red Bull example. I'm just gonna keep drawing back to the Red Bull example. So it would be an illustrative purposes, because if we just talk about the concepts, then perhaps it is not as solid as if we talk about the examples as well. All right. Alright, by the end of this video, let us take a Jaeger bomb together, because that would be very fun. But that would be a few minutes from now. I'm guessing this video would be one of the longer videos I've ever made. But, a Jaeger bomb is fun, and I kind of do want to finish this can of Red Bull. Leftover Red Bull is no fun. Anyways, so type 1 errors refers to errors where we reject the null hypothesis, where the null hypothesis is actually true. So, for example, if we talk about, for example, if we look at the Red Bull example, if we take a sample with 50 cans of Red Bull, and then we do a hypothesis test. After the hypothesis test, we have reason to reject the null hypothesis. We rejected the null hypothesis that each Red Bull can contains 250 milliliters of Red Bull. However, it turns out that the population mean is actually 250 milliliters of Red Bull. Then we have committed a type 1 error. On the other hand, type 2 errors are errors that occur if you do not reject the null hypothesis when the null hypothesis is actually false. So you can see the difference between type 1 and type 2 error. Type 1 error is denoted as alpha, type 2 error is denoted as beta. Now this could be very confusing. Why? Because alpha also refers to the level of significance. Alright, so alpha usually is like 5. So if we do alpha, so this is why I think statisticians are perhaps high or drunk or stupid when they came with these symbols. But who am I to judge? I am just a lonely uni student talking to a camera at 9:40 p.m. on a Wednesday night. Most of the people are outside doing whatever people do on a Wednesday night. Anyways, so yeah. So for example, if I fail to reject the claim that Red Bull cans contain 250 milliliters of Red Bull, so I accept the null hypothesis. However, it turns out that the mean population volume of Red Bull is actually not 250 milliliters. Then I have committed a type 2 error. And we could calculate the probability of a type 1 error, which is usually just alpha, and also we could calculate the probability of a type 2 error. Now, we're not going to be doing that, however, you just need to know that you are able to calculate that. Now, the probability of type 1 error is actually just equal to alpha, okay, which is equal to the level of significance. So alpha is equal to the level of significance. It is also denoted as type 1 error. All right, possible errors in hypothesis test decisions. That's where we could see this table that really handily illustrates our concept. So as we can see right here, do not reject H naught. When H naught is true, that is the correct decision. However, if H naught is false, then we have committed a type 2 error. If we reject H naught when H naught is true, then we have committed a type 1 error. And if we have rejected H naught, but H naught is false, then we have done a correct decision. So that's a table that really illustrates that. Alright, factors affecting type 2 error probabilities, as you can see, is right here. So just know that. Okay. Alright, let's talk about hypothesis testing. So there are two main types of hypothesis testing that we're going to be talking about today. So the first is when standard deviation of the population is known. So if the standard deviation of the population is known, and we are testing for population mean, then we could use the z-test. However, if we do not know the population standard deviation, then we need to use the t-test. And if we use the t-test, we have to introduce an additional variable called the degree of freedom. So the degree of freedom usually, as a general rule of thumb, it is the sample size subtracted by 1. However, in some cases, for example, in paired or two-sample hypothesis testing, the degrees of freedom would be a sample size n minus 2. However, for one sample hypothesis testing, uh, one sample hypothesis testing, degrees of freedom would just be n minus 1. Okay. So two-tailed test. All right. Okay. So another thing to take note, the two-tailed test is that when we are doing two-tailed tests, that means when we are doing two-tailed tests, when we are doing hypothesis testing with no hypothesis containing not equal to signs such as this one, then we have to divide alpha by 2. Why? Because as we can see right here, there are 2 rejection regions. If we only have one side, then alpha would just be one side. However, if we are doing not equals, or alpha not equal, then alternative hypothesis, or alpha equal, then alternative hypothesis of alpha not equal would have 2 ends. And so, because distributions are distributed normally, whether or not whether it is a normal population or whether or not or because a central limit theorem takes place, then we have to divide alpha by 2 to get 2 sides. So therefore, the z critical values will be z negative z alpha divided by 2 and positive z alpha divided by 2. So this is a standard normal distribution illustrating the example. All right, let's just quickly look at an example right here. So we have the question of test the claim that a true mean diameter of a manufactured boat is 30 millimeters. Given alpha of 0.8. So alpha of 0.8. All right. So first of all, the first step, as we talk about in hypothesis testing, is we have to state the no and alternative hypothesis. One of the problems that we talk about, one of the common errors people make in writing down no and alternative hypothesis is that people would do x bar equals 30. That is incorrect because we know the sample proportions and we also know the sample mean. What we are testing for, is we are using sample statistics. We are using sample data to infer proportions and infer the mean of the population. So instead of writing x bar, which we already know, we need to write the no and alternative hypothesis as mu. Okay, as I talked about at the very beginning of this video, Greek letters always refer to population. So mu equal to 30 and mu does not equal 30. Okay, so this is a two-tailed test. Secondly, we specify the desired level of significance and the sample size. Okay, so desired level of significance, 0.5. So if this is a two-tailed test, which it is, then we have to divide alpha by 2 for each side of the z-test. Okay, and then, this is sigma. So this is standard deviation of the population as given at 0.8. And n of 100. That means we have a population of 100. Now keep in mind, when n is greater than 30, then the central limit theorem will come into play. N is greater than 30, therefore the central limit theorem comes into play. Don't worry, I'm drinking water. I'm not drinking any more Red Bull. For tonight, I was thinking of doing a Jaeger bomb, but no, not on a Wednesday night. I knew Alright, let's take alright, let me put this can of Red Bull in my refrigerator really fast so I could drink it tomorrow instead of tonight. It was a bad idea. Terrible idea, even, to drink Red Bull at such an hour. Sacrilegious, even. Alright. Right, step 2, level of significance as well as the sample has been talked about. Okay. Step 3, because sigma, which refers to the population, standard deviation is known, therefore we use the z-test. Okay. For alpha equals 0.05, critical values of z divided by alpha divided 2, values is 1.96. Alright, how did we know this? How the hell do we know this? Alright. First of all, alpha equals 0.05. Let's go to Excel. So alpha equals 0.05. Z-test. Right, that's not right. All right, so what we are doing right here is alpha is 0.05, and we have to divide 0.05 by 2. Why? Because our population has two sides. It has the left side and the right side. So 0.05 divided by 2 is 0.025. Okay, so that means 0.025 of the alpha is the rejection region. Now, we have to find the critical values. Now, we can find the critical values using a table, using a z-value table, or we could use critical values to find using Excel. So norm, because this is a normal distribution, that S that inverse, 0.025, that would give us the left side, okay? Norm.S.inverse, and then the right side, 0.975, that will give us the positive side. So what this tells us is the rejection region. If our test statistic is left of negative 1.95, or negative 1.95996, or right of 1.95996, then we have to reject the null hypothesis. All right, so that is what we call the critical value. So step 4 is determining the critical value. Step 5 is collecting the data and computing the test statistic. So suppose the sample mean is of x bar is 29.84. So this is out of the 100 sample, we come up with the diameter of 29.84. Whereas we want to prove that the bolt is dirty, we come up with 29.984. So we have to see if this is statistically significant enough for us to reject the claim. Using the t-stat, z-stat, we can calculate this. So let's use the z-stat right here, equals z-test. So we'll be able to calculate that, and then we get the z-stat of right there. So the z-stat right here is -2. Now, -2 lies more left or more negative than the critical value, than the rejection region. Therefore, it is within the rejection region. Therefore, we reject the claim. Therefore, we reject the claim. So as we can see, okay, yes. Therefore, we reject the claim that the diameter is dirty because using the hypothesis test, it is more left than the rejection region. Is within the rejection region. From this information, we can conclude that the confidence interval. We can also calculate confidence interval. Alternative to the critical value approach is the p-value approach. This probability value approach, the p-value refers to the probability of getting values that are shown within the x bar. So this is the p-value approach. P-value approach for hypothesis testing. Okay. Calculating p-value. All right, two tails when sigma is unknown. So previously we talked about two-tailed tests when sigma is known. However, when sigma is unknown, as I previously alluded to, we have to use an additional factor called the degrees of freedom. So when sigma is unknown, we replace the sample standard deviation and switch it using the student's t-distribution, allowing for extra uncertainty with the degrees of freedom n-1. Assumes population follows a normal distribution, or sample size n is large enough for the central limit theorem to apply. So here's an example of the two-tailed test. You can pause the video and look at that. Right. For one-tailed test, it is very, very similar. The only difference is that we do not have to divide alpha by 2. So there we go. And here are some of the Excel functions that we're going to be looking at shortly. All right, let's look at the Excel file right now. Okay. All right. So we previously in week 7 we talked about confidence intervals. So we have upper and lower confidence intervals. All right, let's look at question 1. These are the formula list right here. Okay. For a population of internet users, the amount of time each person spends per day sending emails is known to have a standard deviation of sigma 2.5. A random sample of n equals 25 is selected. Okay, so if that is selected, what is the standard error of the mean? So this is the standard error. What is the decisions or assumptions in order to have to calculate the confidence interval to perform a hypothesis test? So first of all, we see that n is equal to 25. Now, since n is less than dirty, we have to assume that the population follows a normal distribution because the central limit theorem cannot kick into play. if a sample of 10, if a sample mean is 10 minutes, sample mean, so x bar equals 10 minutes, calculate a 95% confidence interval for the population mean. All right. So, right, so n equals 25, alpha is 0.05, and we want to see whether or not, we want to prove whether or not the emails sent has equal to mean of 9, or if it does not, then we have to accept the alternative hypothesis. So this is where we do the z-test. First of all, this is the rejection region. If it is left or right of this, then we have to reject it. Then we do the test statistic. So the z-stat comes out at 2, and because 2 is more extreme than the z-stat, we have to reject the null hypothesis. So this is as you can see right here. Okay, so that's the first one. The second one, this is where we do not know the standard this is where we do not know the population standard deviation. So this is why we have to use the t-test. So instead of using z.in or norm.s.dis, we have to use t.inverse to calculate the t statistic. All right, I want to go back to look at the procedures and the steps for hypothesis testing. So whether or not it is a z-test, whether or not it is a t-test or z-test, a one-tail or two-tail, they all follow the same exact procedures of hypothesis testing. Stating the known alternative, choosing a level of significance and sample size, determining the appropriate test statistic, z-test or t-test, determine the critical values, identify rejection and non-rejection regions, collecting data, computing test statistic, computing test statistic and see whether or not it falls within the rejection or acceptance regions, made a statistical decision, state the managerial conclusion in the context of the business problem. So, okay. Alright, so I think I've gone through most of the concepts for week 8 of BUSS1020. I do hope you took some value out of it. It is very a cornerstone out of the 1020 content, and I'll see you guys next time. Take care and goodbye.